Welcome to this explainer. Today, we're diving into an incredibly fascinating theoretical framework developed by independent researcher Dr. Rihan. We're going to impartially unpack what's known as the Rihan atomic model, or RAM for short. And specifically, we'll be exploring how this framework attempts to solve one of the most stubborn and magical mysteries in modern physics, superconductivity.
Just picture this for a second. What if electricity could flow forever, without losing a single drop of energy to heat or resistance? We're talking absolute perfect energy efficiency. We're talking floating magnets. We've actually known about this phenomenon for quite a while, but here's the catch. High-temperature superconductivity remains a massive unsolved puzzle in standard physics. How are these materials actually pulling this off?
So, here is our roadmap for today's explainer. 1. The superconductivity mystery. 2. The Rihan atomic model. 3. A new kind of pairing. 4. The Meissner effect explained. And 5. Predictions and future testing.
Part 1. The superconductivity mystery and the absolute limits of standard physics.
For a material to be considered a true superconductor, it basically has to do two specific things once it drops below a critical temperature. First, it has to exhibit literally zero electrical resistance. And second, it has to display perfect diamagnetism, which essentially means it completely expels external magnetic fields. Now, standard physics leans heavily on BCS theory and something called phonon-mediated Cooper pairs to explain this in conventional materials. But the math, it totally falls apart when we try to apply it to unconventional, high-temperature materials like cuprates.
Moving to Part 2, the Rihan atomic model, which offers us a completely new perspective. To understand Dr. Rihan's framework, we actually have to stop thinking of atoms as those rigid little solar systems with point-like electrons that we all learned about in school. Instead, RAM proposes that we visualize them as dynamic, elastic, and highly compressible magnetic balls, kind of like Russian nesting dolls made of envelopes or Gaussian surfaces for both protons and electrons. According to the theory, these structures are governed by two major forces: net momentum velocity balance, or NMV, and mechanical electrostatic equilibrium. When you look closely at the microscopic dynamics in this model, things get pretty wild. RAM visualizes protonic surfaces revolving at roughly 158 kilometers per second, and the electrons, it treats them not as little dots, but as relativistic spiral string-like entities moving at nearly the speed of light. The paper itself actually describes them using a sperm analog, tracing out these ovum-like Gaussian envelopes in continuous revolution, which keeps everything compliant with Heisenberg's uncertainty principle. So you have these highly compressible surfaces traced by incredibly fast strings, naturally setting the stage for large-scale quantum coherence.
Section 3. A new kind of pairing, or how we go about building the superconductor. The contrast between the standard framework and RAM is striking. Conventional BCS theory relies entirely on phonons, which are basically quantized sound waves in the atomic lattice, to push electrons into pairs. RAM interprets this pairing totally differently. It views it as the synchronization of two spiral strings, actively glued together by the elastic vibrations of these compressible magnetic balls. Under RAM, forming one of these pairs follows a very clear three-step sequence. First, as the material cools down to extreme temperatures, thermal broadening, all those random heat disruptions, drops significantly. Second, this extreme chill allows tight net momentum velocity synchronization to happen across neighboring atoms. The strings essentially sync up their rhythms. Finally, the vibrations of the Gaussian surfaces act as the glue. A local distortion in one atom's envelope physically propagates to its neighbors, retarding the natural repulsion between them and creating an effective attraction. The result is a composite bosonic-like entity.
So why does all of this result in zero resistance? Well, because these spiral strings are perfectly synchronized in their net momentum velocity, they achieve minimal scattering. Their synchronized revolution completely minimizes any momentum exchange with the surrounding atomic lattice. And no electrons scattering off the lattice simply means you get that magical zero electrical resistance.
Part 4. The Meissner effect explained. Let's look at perfect diamagnetism.
Standard physics models rely on highly complex mathematical explanations for the Meissner effect, but RAM takes a surprisingly geometric approach. The model proposes that the very nature of these revolving Gaussian surfaces means they naturally generate persistent electrical currents. So when you introduce an external magnetic field, the atoms don't just passively sit there.
Instead, that external field induces a collective opposing precession of the electronic strings across the entire lattice.
This collective motion actively expels the magnetic flux via Lenz's law, and the really fascinating part? RAM states this expulsion is massively amplified by the relativistic speeds of the strings. Remember, these entities are moving at nearly the speed of light. The threshold where this effect finally breaks down, the critical field, is directly proportional to the stiffness of the Gaussian surfaces.
And finally, Part 5, Predictions and Future Testing. Can we scale this up to room temperature?
How does RAM adapt to the real-world materials we test in labs? Well, from metallic superconductors like mercury, the model points to their closer atomic packing and moderate Gaussian diffuseness. This correctly yields a low critical temperature of about 4.15 Kelvin. But then you have the mysterious high-temperature cuprates. For these, the model leverages their layered, highly compressible perovskite structures. Their directional Gaussian overlap and string helicity allow for much stronger superexchange. And nonmetals? According to RAM, they just lack sufficient diffuseness for this kind of pairing to happen at any accessible temperature.
All of these concepts build into actual, testable physical predictions. RAM suggests that if you apply extreme pressure, you force these magnetic balls closer together, which enhances their overlap and raises the critical temperature. This aligns perfectly with what modern labs are observing with high-pressure hydrides. On top of that, the physical deformation of these balls neatly explains flux pinning in Type II superconductors. Most exciting of all, if we can engineer materials with precise Gaussian widths and string tensions, we might just unlock true room temperature capability.
Dr. Rihan actually wraps up the paper with a rather profound, ambitious statement, writing, "This extension strengthens RAM as a candidate for unifying atomic, condensed matter, and potentially quantum gravity scales. It is a massive goal, attempting to perfectly bridge the microscopic geometry of a single atom with the macroscopic quantum magic that we observe right in front of us."
As future research pushes forward into detailed numerical simulations and ultra-fast spectroscopy, we're left with a massive question to ponder. Will rigorous experimental testing prove that synchronized relativistic strings and elastic magnetic balls are indeed the key to our limitless energy future? It is a radical way to view the fundamental building blocks of our universe, and it just might change everything we know about how power flows. Thanks for joining us for this explainer, and keep questioning the physics around you.